Hello everyone, welcome to questions and answers based on lectures of Computational Finance. Today we have question number 9, which is based on materials covered in lecture number 4. The question of today is, what is the implied volatility term structure? This question often appears in my courses when I'm asking students, what would happen to the Black-Scholes model if you would make, instead of having constant sigma, constant volatility, you would assume volatility to be time dependent. So in the Black-Scholes model, we have a constant, but instead of constant, we consider time dependent. Will this Black-Scholes model with time dependent volatility be able to generate implied volatility, smile, or skew? An answer often is, it is possible to generate smile and skew. And this is unfortunately wrong answer. So this question about the term structure and also connection between sigma in Black-Scholes model to time dependent, those are closely connected. So let's take a look first what is implied volatility, how those are calculated, and what does it mean actually to take consider time-dependent volatility in the Black-Scholes model. So in the standard Black-Scholes problem is to have, if we have a prices and we have a market price for call option in this case, we have a Black-Scholes price with unknown volatility sigma, then by inverting this equation or finding sigma imp such that this difference would be 0, this is essentially the definition of the implied volatility. So if we look at on the left-hand side prices, on the right-hand side implied volatilities, we see that this is a call option price, so it's a call. We see that it's a call option prices are going downwards towards 0 for increasing strike K. So this is strike K, and this is the corresponding Black-Scholes implied volatility. So it's easy to see that this implied volatility and also the prices are calculated based on the Black-Scholes model with constant sigma. Sigma here in this case is equal to 0.2. On the other hand, if we look at the market, in the market we see also prices of call options going down towards 0 for increasing strikes. However, implied volatility, it is behaving completely differently. So first important message here is that if we compare option prices from the market versus the option prices from the model, it is very difficult to judge based on option prices whether there is an implied volatility, smile, or skew. You see this shape very much resembles the shape from the market, although implied volatilities in this case are flat. In this case, there is a skew in the market. So this is the very important information, that always look at implied volatilities. If we want to judge about the implied volatility, smile, or skew, never look at the prices, because prices, they have, you cannot really invert this formula yourself to draw a conclusion whether there is a smile or skew. And now, if we also look further, what are the possible shapes of implied volatilities? So now here, in this case, we considered implied volatility skew. However, there are also other possibilities. Implied volatility smile. Here's the skew that we have just seen. And also we could have a hockey stick. So you see it resembles a hockey stick. So there are multiple different shapes of implied volatilities. And once you deal with market data, then you will realize that there are many different shapes of implied volatilities. Depending on type of a market, then you will experience different shapes. And of course, correspondingly, you will need to find different models and different calibration procedures to calibrate to those implied volatilities. But if we go back to our problem of a term structure, so here's important to keep in mind that now we are looking at the maturity. So we have a fixed strike and we are varying expiry of options. If we consider Black-Scholes with time-dependent volatility, so not stochastic, but just time-dependent, so instead of sigma here, we have a sigma t, then we will see that this is the case for sigma constant, this is the case for sigma time-dependent, and there will be no smile in both cases. So implied volatility, the term structure, tells us how the volatility changes for at-the-money options in time. If we change the expiries, how this evolution of implied volatilities goes in time. However, there will be no smile. So actually, if we will look at the 3D picture, 3D plot, we will see that for every strike is the same implied volatility, because it's for every point t, this number is just constant. However, if we change implied volatilities, the expiries, then we will see implied volatilities will change. And that's called implied volatility term structure. if we look at the money options, at the money implied volatilities, so we take only one fixed strike, and we only look at this implied volatility for moving expiry, changes expiry. That's the definition of implied volatilities term structure. And be aware that if we add time dependence in the Black-Scholes case, that will not generate implied volatility smile or skew. You still have Black-Scholes model with no implied volatility smiles or skew, but you have only term structure that only allows you to calibrate to add the money options. In the book, I have, and also in the lecture number 4, you will find materials how you can relate, actually how to find prices, option prices, call option prices and put option prices based on time-dependent volatilities. You can actually represent nicely this actually by so-called sigma star. So actually you can compress this time dependence into some constant sigma for a given option, and then you can still reuse the Black-Scholes pricing formulas. So this will be it. So keep in mind, time dependence does not generate smile or skew. It only affects at the money volatilities, which are actually associated with a term structure if we look at the time dependence, not strike dependence, but only the expiry dependence of options. Okay, I hope it explained, and see you next time. Bye-bye.